Think forward. Think Research Channel.
Since 9/11, this country has been proactive in providing a more secure homeland. The invasion of people's civil liberties is a high concern.
I think the concern about privacy is legitimate, and there is a technological solution to it.
You want to keep the authorized person out of the video, so how do you handle interactions?
Samsung actually has the ability to erase those actions.
My goal is try to tell the community there is a way, and then ask also other people to join me to work on this. So I think it's a very important problem.
The research that Samsung conducts is very much complementary to the research that we're doing in terms of surveillance, in terms of tracking of iris that Dr. Yang does. Samsung is working on the other side of things, which is to help people who are in such environments preserve their privacy. So I have great hope for the research that Samsung is conducting.
He's finding ways to engage in surveillance, develop surveillance technology, which can be encrypted and which can focus on the potential threat or perpetrator and not include the information on innocent bystanders or people not of interest. And so this is going to protect their rights to privacy when we have to engage in broad surveillance and a range of places where people have normally a presumption of privacy.
What I am trying to do is that I'm trying to go from a technological point of view, saying that, well, there is a way to protect personal privacy and yet also able to provide the increased security that brought forth by other surveillance technology.
If I'm a trusted member of this center or any building with such a network in it, then I have no fear that my day-to-day actions will end up then in a case where there's been some crime or some act of terrorism perpetrated.
Samson's research in visualization technology is differentiated from the other research in that field through this interdisciplinary partnership and collaboration between the University of Kentucky and Morehead State University. Our faculty in political science and constitutional public law are working with computer science and engineering here at the University of Kentucky in ways that help both and contribute to both fields.
I think a lot of people now go for there are sort of unnecessary debates or upheaval that people think that their big brother is watching. Okay, and there's no way to do it, and no way to do it except for just dismantle all the surveillance and go back to the to 20, 30 years ago where there is no surveillance. However, I think we are entering an era such that those technologies are absolutely essential of protecting our country. So the first problem, as you said, is the removal of people, or in general, I would call it sort of video modifications for privacy protection. So the goal is that we are trying to change the video to either delete the people or obfuscate the human subject whose privacy we want to protect. And graduate students play a very important part for this project, because they are really the persons who are in the trench to actually doing the groundwork. So and I have a lot of fun working with them. I mean, they're all bright students, and hopefully by sort of working with me and then they're working on their own research, they can learn to become good researchers, and then they can want to accomplish the academic goals they set for themselves.
We want to keep authorized people working in an indoor facility, for example in an office, to be on the video, and we want to just have the visitors. So we want to remove the people who are just working daily in an office. So we need algorithms to erase or remove objects in images and in video in the surveillance. So how do you handle interactions? Can you do it faster? Can you do it better? And more importantly, can you do it in a perceptually consistent way? So as a human observer wouldn't find that you have modified the video or the image. So these are some of the challenges that there are in this project.
We mainly try to make our system a real-time system that is right now no one has done this before, and because there are so many calculations in all the algorithms right now, they cannot deal with real-time stuffs.
We don't want the video to actually leave the premise of the camera. We want to do it as close as possible to the camera so that no tampering can be done. So it is important that we can do it fast and do it close to the mirror using embedded processors and things of that sort. To erase anything in the video, we have to first find out where this person or where this object is. So since most of the times an object actually move around, we have to be able to correlate from frame to frame about the locations of a specific object. So that's the idea of an image tracking. So a video consists of one frame, second frame, and third frame, and so forth, sort of displaying them temporally on a monitor. So by comparing successive frames, you'll be able to identify which part of the frame is moving. That corresponds to the foreground. Everything else that's not moving is the background. The process is that we are basically doing a correlation analysis between successive frames. We first identify what pixels are moving. This is the first step. And the second step, after we know what pixels are moving, we group the pixels together to form an object. And if pixels are moving together, most likely, because they follow the same motion, they're likely to belong to the same object and have similar colors and whatnot. So that is a basic process that we use for tracking an object over a long period of time. Our team back in Lawrence Livermore have identified an algorithm to track objects of many different types of speeds. So this is particularly applicable for traffic video, traffic surveillance video, where there are cars that are stopping momentarily in front of the red lights, but their car may be running very, very fast. And we are building a very robust algorithms to adapt to different speed and also to different weather conditions, nights, bright lights, or raining, snowing, that's different conditions. So that's one part of the work. Recently, after I arrived at UK, we have also working on some of the tracking for human beings. Human beings is different from cars. Cars don't usually change shape, or at least change a little bit, different depends on our perspective. However, human beings change shapes a lot. I mean, when you walk, your hands move around, your legs move around. So this is a very different problem than tracking cars. And so far we have built up some tracking algorithms for monitoring of persons in indoor environments over kind of a large area. Two of my students, Vijay Venkatesh and Jane Shah, they are working on image tracking. So they have built there are a number of systems they already started building on. One of them is we're able to track human face within the camera. So that's one part of it. The other one is that we're able to track sort of the entire human body over a wide area. So today we come to the library to capture some realistic video surveillance inside the library using multiple camera setups. So we have two cameras to hook up to the computers. We also have a high-definition camcorders that give a much wider view of surveillance.
As a librarian, I'm really interested in the security of our materials. And so we invited Samson to come in and use our reading room really as experimental lab space to videotape our space and our patrons and our materials, and kind of use that as experimentation to determine if he could apply his research in a real-world setting. We're particularly interested in that because we have security concerns in our reading room with our very rare and unique materials, and so we're hoping that some of his solutions will be applicable to our situation. And we're really looking forward to seeing the results of his research and hopefully applying them in our specific situation.
Well, now we have the data, we have to go back to the lab, and then we start to processing. We need to try out our existing algorithms, see where and when it breaks, and then from there we will, hopefully come up with something better to take advantage of the multiple camera setups that we have tried today. And hopefully in the future we're going to have a more realistic system that actually set up in this library or perhaps in other library, in this university and other places as well.
The existing research, what they do is they try to obfuscate the object in such a way that you would see a person but you wouldn't see the face. They just blank it out, or they just put a block on the face or the whole person so as you won't appear in the video.
What they do is actually they have human beings using in a control room using a joystick to move around a particular area of 30 pixels following the faces of a person. James has been working on a technique that's completely automated, and it automatically identifies where the faces are and then blur them and then try to follow. If there's a person move around, he's trying to track the person's face and then continuously to blur them.
Right now, for the face detection stuff, the problem is how we can locate the face accurately. That means precise know the location of the face. Right now, we have some techniques that can recognize the face from the front view, but when the face rotates in a certain degree, the detector may fail. And also, there are all kinds of faces with head, with glasses, and maybe they have some other stuff on the face that will fail the detector also. So we try to make some improvement in the face detector. And then another problem is when we blur the face, it gets artificial in the tape. So it makes people think the tape is destroyed or something else. So we want to make it natural, but also hide the identity of the person.
But what we are trying to say is that gives a clue to the person. For example, if you know the person, by just observing the blackout box, you can somehow find the gender of the person, you can identify the habits of the person, and so on, so that you can get a clue of the individual that's on the video. The new thing that we are trying to do is we are completely erasing them from the video so that you don't know even the person is there, but still we preserve the original copy by having them as a watermark in the same video. When you're trying to modify a video, I mean, it's going to be, the first one is you want to remove some person from the foreground, but when you remove that, you need to fill that with the background. What we have is that we have background models of, since we observe the scene for a very long time in a surveillance video, we have a good description of the model. So the video completion becomes a two-part problem. One, you want to remove the individual person, and then you want to complete the missing regions.
But what if there are something going on behind that objects that you want to remove, behind the person that you want to remove? Well, then what you need to do is that you have to preserve the particular dynamic motions of the object behind the occluded object, so that when people look at the modified video, they will not notice anything out of ordinary. So to do that, we basically look at the the video before and after the occlusions and try to build a model of the motions of the occluded objects behind the objects that we try to remove.
If for example, if a person is walking through an obstacle, you just want to remove the obstacle. So, but you don't have the missing regions. So the video in painting problem is foreground filling. First of all, you need to predict how an object would move and fill it completely. So that's the main part. And then if you want to remove something, then you need to fill that with the background. So that's another part. So these are the two important parts that are in video in painting.
We have an algorithms basically allow us to take advantage of various properties of the object shape so that we are able to reconstruct the shape of the object even under heavy occlusions, like half of the object is being occluded. We're trying to guess the other half. So we get reasonable success. If the object possesses certain levels of symmetry, then we are able to do a reasonably good job on figuring out what is the shape of the object.
In completing objects, I mean, when you are trying to fill a foreground object, you want to predict how the object moves. So first you want to complete the structure of the object. You want to know, for example, if a hand moves, you want to complete the hand. The human structure is a symmetry on both sides. So you want to be able to complete something which a camera looks at an angle. So that's one important improvement that's going to be happening within a short time. Currently existing algorithms, image in painting algorithms in particular, do not take into account the symmetry of the existing contour to fill in the missing portions. What they do is that they just try and use the local information so that they want to just complete the missing information. It doesn't work well. So just by looking at it, you can say that, no, this is not how it looks like. We want to have a global completion. So what we do is that we understand the entire curve and we say that we identify first its symmetry. And then we use the symmetry as a cue to rotate the object and complete the missing portion in such a way that it looks perfectly symmetrical.
Right now there are some works on video in painting, but they are all doing a very simple environment that is only a very few people and very few objects in the scene. We want to deal with very complicated things and with all kinds of occlusions and all kinds of perspective changes. So that is mainly our goal, and we also want it to be done in real time.
Okay. Things that are not easily predictable, that we have a hard time coping with that. And also, we have only able to so far handle video with only two objects. Okay, when you have multiple objects, the levels, we have to figure out what person is in front and what person is in the back. Multiple objects become a lot more challenging problems, and we are looking at that as well. Getting into the sort of arena of actually changing the video, this have quite a few consequences. When we are dealing with data, sensitive data like a surveillance video, which have the potential to be used by law enforcement or in a court of law, then their truthfulness becomes very, very important. If I can come along and change the video using whatever technique, other people can do exactly the same thing. So we need to kind of authenticate the modifications, that the authentications can only be done by sort of a single party that belongs to where the ownership, who owns the video. And on top of that, it has to be very secure that any tampering, immediately the owner will notice, will be able to identify there's any sort of tampering of the video.
The ability to hide images of innocent persons, if you will, or innocent bystanders, so that you focus only on the suspect in a video, is very important so that you protect their civil liberties. However, in order for this to be admissible, you have to have the original authenticatable video product.
So we also have students who are working on this particular projects. What it's trying to do is that we're trying to use the original video as an invisible watermark and embed directly to the modified video, so that later on, if this particular piece of modified video needs to be used in a court or by the police officer, with appropriate decryption key, the owner can authorize the police to extract the original video so that the original scene can be observed.
So there's a market for the product without the encryption, which allows you to authenticate the original video. But the value for Homeland Security is what's critical for the encryption, because that's going to make the original admissible in court. And I think that's where it has the highest value for law enforcement and Homeland Security purposes.
So video watermarking works like this. You have to have what is called a watermark, which is the data that you want to hide in an image. So right now, our watermark is the original image. Okay. So the way that we hide this is that we first of all we shatter the watermark into thousands of pieces. Okay. And then we put into the image into the area that are not quite visible to sort of casual looking. Areas such as the very bright area that have very high texture, very busy. When you modify maybe 1 or 2 levels in those pixel levels in those areas, to casual viewing, you would not be able to see any difference. However, we're using these characteristics to take advantage of our human eye and then try to put hidden information there. Our watermarking system goes hand in hand with video compression. There are 3 steps in a video compression algorithm like MPEG or H.263. There's motion compensation, discrete cosine transform or DCT, and entropy coding. Motion compensation and DCT compress the video by removing image information that our eyes cannot see. Entropy coding is similar to regular text file compression. We first use the DCT to identify unnoticeable pixel areas within small image blocks and then combine them together to form a global visibility mask. We use a fast sorting algorithm to identify the brighter areas where we can store invisible information. Then we insert the encrypted watermark in those areas using parity embedding. The final video is run through the normal entropy coding process to create a final video stream. One key advantage is that the final watermark video is a fully compliant MPEG file and thus can be viewed using any video player with no new software required. Well, the data that we put into the image doesn't have to be an image. It can be anything. So you can use that for authentications. You can, for example, put your company logo or any trademark or patent ID, whatever. And then you shatter them into many bits, and then you hide it in an image. So you can use that for authentication, right? You can use that to prove that this image actually belongs to me. The techniques are originally developed for small amount of data. However, to operate on images and video, we require the computers to run a lot faster so that we are able to handle the huge volume of images and data. And cryptographic technique right now is just not able to do any of that. And so we need to devise new technique to do so. Well, first we have the first video object removal system. Right now it's still kind of running slowly, but then we demonstrate that it is feasible to remove certain objects, track it, remove it, and replace it. So that's the sort of major accomplishment. We are doing a reasonably good job on hiding the original videos in the modified video, such that we have conducted some of the perceptual experiments, and basically our subjects said that even after the embeddings or storings of the hidden informations into the video, they really cannot tell the difference that we are hiding something inside. So that's good. That's one of the major accomplishments last year.
I have been working at this problem of skewed symmetry completion for about a month, and I'm just thinking about it all the time. And the greatest enjoyment that I derive is that I know this has not been solved. And if I can solve it, I think that's going to be the key. And solving some problem which has never been attempted just gives me the greatest satisfaction.
There's no one did on the world except us. So I think this is the most exciting thing.
It's important to demonstrate to not only to the research community but also to industry that these things is feasible. This thing can be done in real time using relatively cheap hardware. So we want to do that. This is one of our sort of ultimate goal. Part of it we can do already. I told you earlier that the face blurring technique, we can do it reasonably fast. We can do it real time. Other things, the watermarking, the actual object removals, those things are a lot harder to do in real time. And we hopefully, in about maybe 2 to 3 years' time, we're able to understand the algorithm well enough, understand the problem well enough, and then do our optimizations and get it to run in a sort of real-time platform. We're having a lot of fun. Essentially, it's that we are learning the needs of different people. We are doing what I think that there's a certain need in a society, and yet we're able to invent, we're able to create.
I think it also provides a very important differentiation for Samson's research from what other people in the field are doing, because he is conducting interdisciplinary research with faculty members from other disciplines that can contribute to the legal and constitutional considerations that really are at the heart of the contribution his technology is going to make to government and homeland security policy.
There's nothing bring me more joy than, in the late at night, I figure out something that I believe that I'm the first person in the world to figure that one out. I mean, that's sort of the eureka moments is priceless, and I think that is the sort of things that drives me and give me most joy in my work.
I believe Samson's technology is going to provide an invaluable tool to government to provide greater protections for civil liberties of individual citizens, and the pervasive adoption of surveillance technology is inevitable, I think.
What we hope will happen then is, in addition to the basic research and the tough questions from a technical standpoint that Samsung and his students are answering, we hope that we will see new industry created around some of this research. In particular, I can see products, I can see markets coming out of Samsung's lab. The surveillance video, the removal of people from that and then encrypting that into a watermark is just one of the things. Another project that he's working on, which has tremendous commercial potential, is the video and audio Google mechanisms that he's developing in the lab. And then a final product, which may even eclipse those two, is his secure image processing.
The Visualization Center is a wonderful place to work. It brings a lot of researchers in our area together so that we can collaborate. There's a lot of synergy going on between myself and other faculties and as well as other researchers here. And also it provides a place that all the students can also talk to each other, especially students working in similar projects. And of course this is an ongoing work, and so my goal is try to tell the community there is a way, and then ask also other people to join me to work on this. I think it's a very important problem.